So as Pietro said, I'll be talking about group field theory. Today I want to focus mostly on foundations, and then in the next lecture, I'll start talking about condensates in group field theory and their relation to cosmology. So my goal today is really to introduce the underpinnings, the foundations of group field theory, starting from scratch and motivating it from loop quantum gravity. I'll stop when I'm about halfway through these slides for questions, and then of course again at the end. So let me start with an introduction explaining where group field theory comes from. So here again, I know that these are a series of mini courses this summer school on loop quantum gravity. And so I'm going to focus on motivation coming from loop quantum gravity, but I think it's important to keep in mind that there are links between group field theory and many approaches to quantum gravity. So in particular, loop quantum gravity, but also other approaches like dynamical triangulations, also the matrix models that are used for two-dimensional quantum gravity, and then their generalization of tensor models. So I'm going to come from the perspective of loop quantum gravity. And in this case, the most direct connection between group field theory and loop quantum gravity is through spinfold models. So as you've seen in the series of lectures by Maite, when you have a spinfold model, you have a transition amplitude, which is given by a sum. And in this sum, each contribution corresponds to a certain diagram interpolating between the initial and final state. And I'll say a little bit more about this later on. But you can clearly interpret these diagrams as some sort of Feynman diagrams. And so then a very natural question to ask is whether there's a field theory that generates these Feynman diagrams. And the answer is yes, and that's group field theory. So this is where group field theory comes from, at least from the perspective of loop quantum gravity. And this is how I'll start in these lectures, showing this connection in a little bit more detail. Now, of course, once you have the group field theory, you can just use the standard Feynman expansion, and you get back the spinfold amplitudes that you started with. So everything is consistent. But of course, this isn't the point of group field theory. So of course, you can recover the spinfold model, but the other thing that's nice is that once you have the group field theory formalism, this is a quantum field theory formalism, this opens the door to other calculational tools. So of course, if you have a spinfold model, you can do calculations that are perturbative in the number of foams that you consider. And these calculations can be very useful, but of course, depending on the calculation that you're interested in, sometimes other techniques are more powerful. So sometimes you don't want to do a calculation which is perturbative in the number of essentially Feynman diagrams. And one example that we'll see is group field theory condensate cosmology. And so this will be the next lecture. And so we'll see there that we can study the collective dynamics of condensate states without calculating any spinfold amplitude. So here the calculation is done in a very different way, as we'll see in detail. So in this first part of the mini class, I'm really going to focus on the relation between loop quantum gravity, spinfold models, and group field theory. So a lot of what I'll be saying today will be explaining how to rewrite a spinfold model in terms of group field theory and vice versa. But I want you to keep in mind that one of the reasons why we're doing this is to gain access to all of the calculational tools that a field theory formalism gives you. So that's one of the big motivations that we should keep in mind. Okay, so the outline of what I'll discuss in this first part is I'll start with 3D Euclidean quantum gravity, so the Ponzano Reggie model. Then I'll transition to the four-dimensional Lorentzian quantum gravity, GFT, so based on what's known as the EPRL, or Engel-Pereira-Rovelli-Levine spinful model. And this is the one, of course, that we're most interested in, because we expect that to describe, gravity. We want to understand four-dimensional Lorentzian quantum gravity. So this is the one that's most relevant for nature. But still, the 3D Euclidean case is an easy place to start and to get a handle on what's going on. And then finally, I'll end by explaining how we can relate group field theory to canonical loop quantum gravity. So the first two parts, I'm really going to be focusing on spinful models and how they're related to group field theory. And then I'll end by explaining, okay, well, we can also relate, of course, to canonical loop quantum gravity, and this is what it looks like. Okay, then the next part of my mini course will be on condensate cosmology. And Valentin Bozem will also give some talks on matrix models, tensor models, some of the more field theoretic aspects, including renormalization of group field theories. So this is the general outline. And let me start with just talking about path integrals for quantum gravity in general. So if we want to calculate the path integral, and here I'm showing the Euclidean path integral for quantum gravity, then what we typically have is we have some initial configuration here, and some final configuration here, and then we want to sum over all paths that interpolate between those configurations. So you have some amplitude given some boundary here, where you're summing over all intermediate paths. Okay, so conceptually, this is very nice. This is very clean. But if you want to calculate anything with this, you need to make this precise. And there are 2 points in particular that need to be made precise. And so the first one is just to figure out what the boundary states are. So of course, in the example that I've drawn here in this figure, your boundary states would be 2 spatial metrics. So an initial spatial metric here, and then a final spatial metric here. But this has to be regulated some way. So to do a calculation, we need to know exactly how do we define these boundary states, what Hilbert space do they live in, questions like this. And then the next step is to figure out what are the configurations for the 4-dimensional spacetime metric that we sum over. So when we do this sum over all possible paths, what exactly are the configurations that we sum over? So this is quite challenging. And so I want to start with a relatively simple case, as I already mentioned, and that's just 3-dimensional Euclidean vacuum gravity. So there is no matter that's coupled. This is just 3 dimensions, it's Euclidean, and we'd like to see how we can calculate a path integral in this context. And maybe just a quick clarification. Here, when I've drawn this picture, I'm kind of thinking in the Lorentzian case where I have an initial state that I start with and I have a final state that I end with. And I'm sort of thinking of time evolution between the two implicitly. So here we're starting with 3-dimensional Euclidean vacuum gravity. And so in this case, the boundary won't be some initial and final slice. It's really just some closed space-like surface. So in this case, you can think of the boundary that shows up here as just some closed space-like surface. Okay. So now I need to answer these 2 questions. What are the boundary states and what are the configurations that are summed over in the bulk? And one proposal for this is known as the Ponzano-Reggie spinful model. And so I'll start by answering the first question, what are the boundary states? And I want you to already start thinking about what will happen in the higher dimensional case. So in 4-dimensional loop quantum gravity, we expect that a boundary, right, will be some sort of spatial slice, that'll be a spin network. Okay, so that's the 4D case. Now let's come back to the 3-dimensional case and think about what will happen there. And in the Ponzano-Reggie model, the boundary states are trivalent graphs. So I've drawn an example here. And each of the links carries an SU2 quantum number J. So, and because these graphs are trivalent, so you can see that each node here has 3 links that lead from it. And that's true for all of the nodes. That means that this graph is dual to a triangulation of a 2-dimensional surface. So you have some 2-dimensional surface, which is possibly curved, and you can just chop that up into a bunch of triangles, and this will give you a discretization of the manifold, the 2-dimensional surface that you started with. And these J labels that are carried on each link, so let's look at this link here, for example. There's a quantum number J that lives there. And what it does is that it gives information about the length of this side of the triangle. Sorry. And so, of course, if we know the length of all of the sides of the triangles, then we know everything we need to know about the geometry. We can calculate all of the angles of each of the triangle and so on. Okay, now you may be wondering, why am I calling this an SU2 quantum number J if there's no M that shows up anywhere? And the reason that there is no M is because there's a gauge invariance at the nodes, essentially imposing that there's 0 total angular momentum. And this ensures that the physics depends only on J. And the way that you can understand the requirement that the sum, the total angular momentum must be 0, you can understand that as requiring that these triangles close. So you can think of the length here of this side actually being a vector, and you want that when you add these vectors together, so you add this vector here, plus this vector here, plus this vector here, you want to come back to the point you started with, so your triangle closes, and this imposes that the total angular momentum has to be equal to 0. And this is why you can essentially throw away all of the M labels. Okay. And finally, of course, we're interested in the curvature. So in 2 dimensions, you can calculate the curvature just by adding up all of the angles that meet within a loop of the graph. So for example, I have this loop in the graph here, right, that's composed of these 5 links. Now, there are a bunch of angles in the triangles that meet here. So I have an angle here, and I have an angle here, and another angle here, and then another angle here, and then another angle here. So I have these 5 angles, and I can add them up. And then depending on how different from 2 pi that is, that tells me about the curvature contained within that loop. So by knowing the lengths of the sides of the triangles, I know the angles, and by knowing the angles, I can calculate the curvature. So this gives me all the information I need in this discretized version of the 2D surface. And these are the boundary states that we'll use. And so if we have, we want to calculate the transition amplitude for some boundary, we express the boundary in terms of these graphs. And again, just to make the contact with 4-dimensional LQG, where we'll go later, the equivalent in that case would be a spin network. Okay. Now, what about the amplitude? So I need to figure out what the intermediate states are that we sum over in the path integral. And here, I'll explain that, and I'll just give you the amplitude right off the bat. So if you're given some boundary psi, then your Ponzano-Reggie amplitude is given by the following form. So first, you have a sum over all of the foams that interpolate between that boundary. And we require that these foams be dual to 3-dimensional simplicial complexes. And what is that? That's just a discretization of a 3-dimensional manifold into tetrahedra. So just like we started off when we were talking about the boundary states, go back and we look at this figure here, we had a 2D surface and we split that up into triangles. We can do the same thing with a three-dimensional manifold. We can split that up into tetrahedra. So we're just doing the same thing except one dimension higher. So what we do is we sum over all of the foams that interpolate, that can form an interior to this boundary, such that these foams are dual to a simplicial complex. So again, dual to a discretization of a 3D manifold into tetrahedra. And then we have a sum over all of the possible SU2J numbers within and in the bulk. And we have a number of products over the faces, the edges, and the vertices. So first, let me tell you a little bit more about these terms that show up here, and then I'll give you more of a graphical picture of this. I expect that you've already seen this in Maite's class, but I just want to go over a few points again, especially the points that will be relevant for the connection with group field theory. So as I said, we already have this first sum here over foams. Then we have a sum over the spins. And then we have a face amplitude, which is 2J plus 1. So that's just the dimension of the SU2 representation on that face. And we have an edge amplitude, which for Ponzano Reggie is just 1. So actually this term here turns out to just be 1. So that can go away. I just wanted to include it for the sake of generality here. This term ends up being just 1. And finally, you have the vertex amplitude. And this is just a 6J symbol. So from your, so when you have a vertex, you know that there'll be 6 faces that meet there. And this is guaranteed because the foam is dual to a 3-dimensional simplicial complex. And from those 6 faces, you have those 6J labels, and you can construct the 6J symbol. So once you have, and this is essentially built from Clebsch-Gordon coefficients. So on the left here, I have a very simple example of an interpolation here. So let's say we have a boundary here where I just have a very simple trivalent graph. So I just have J1, J2, and J3 like this. And then I watch its evolution. So I get this foam here. So you can think of stretching this out. And then I have my vertex here. So I have one edge that goes into the vertex and then 3 edges that come out like this. And then at the end, I have this other boundary. So I still have my J1 and J2 and J3 here, which haven't changed. But now I have this internal triangle here where I have a J4, J5, and J6. And so the Ponzano Reggie vertex amplitude is just the 6J symbol combined of all of those terms together. Okay, and so I don't want to spend too much time on this because I'm sure Maite has already explained this, but in your spin foam, you have these edges, which are these lines here. Then you have the faces like this, a face here, and you have the 3 faces inside here, and then the vertex here. And so associated to each, if I go back here, to each face, you have this face amplitude. Associated to each edge, you have an edge amplitude, which in this case turns out to just be 1, so you can ignore it. And for each vertex, you have a vertex amplitude, which I've given here. Okay, so this is the basic spin foam model. Now the question is, okay, well, what about group field theory? So if we look at the spin foam amplitude, which I just showed you, it's very comparable to a sum over Feynman diagrams, just from a normal quantum field theory. And what you can see is that we can really interpret the spin foam amplitude as a sum over Feynman diagrams, except instead of having particles corresponding to, let's say, electrons, instead now you have diagrams that correspond to some geometry. And in this case, the geometric particles will correspond to these triangles or nodes. So if we go back here, we start off with some number of triangles or trivalent nodes, one or the other. You can view it either way equally well. And those will be the particles that you start off with. And then you can ask, okay, how do they interact? And then you have some final state. Sorry. And so these nodes will follow edges. So you can think of the edges as being the propagators. And then each edge, of course, because it's a trivalent node, it has 3 faces. So each of these particles carries 3 J labels. And then the interactions are the vertices. And here you expect to have geometrically, what's happening here, if you look in the dual picture, is that you have 4 triangles that meet to form a tetrahedron. So here, for example, you have 1 triangle coming in, and then 3 triangles going out, and together they form a tetrahedron. Okay, and what's important here in terms of constructing the group field theory is that these are 4 valent vertices. So in the language of quantum field theory, in the language of Feynman diagrams, what you expect is that you'll have 4 of these particles will meet at a point. Okay, so let me return to the question I started with at the very beginning of the talk. So is there a field theory that generates the Feynman diagrams or the spin foams that arise in the Ponzano-Reggie model? So let's try and construct one. Now, these excitations are these triangles or these trivalent nodes. So it's important to be able to switch back and forth. So I'll often use one or the other, or maybe both at the same time. And they're each carrying 3 SU2 quantum numbers. So it's natural to introduce some field phi, which has 3 arguments. So G1, G2, G3, which are elements of SU2. So this is a field, so it just maps those 3 arguments of SU2 to a real number. Now remember that we have this gauge invariance condition at each triangle or at each node, which essentially is the closure condition that the sides of the triangle close. And what that means is that in terms of SU2, is that you have a gauge invariance in SU2. And so what that means is that if you multiply each of your 3 arguments on the right by the same group element, then your field, the value of your field shouldn't change. And this should be true for any group element H in SU2. So this is the gauge invariance condition. And we'd like an action so that we can define the partition function and calculate what the Feynman expansion gives. Now, the propagator is related to the edge amplitude, which is just 1. So what that means is that the kinetic term, phi squared in the GFT action, should just be trivial. It should just be essentially the identity. And as we saw just on the previous slide, these triangles, they interact by combining in groups of 4 to form tetrahedra. So what that means is that when we look at the GFT action, we want to have a potential term that behaves like phi to the 4th, so that we have these 4 triangles that meet at a point. So by understanding what's happening geometrically, that tells us what the interaction term should be in the group field theory action. So let's start to put those pieces together. I think it's very helpful to show the propagator for the GFT field and what we require for the interaction in a graphical way. So the first part here on the left is just the propagator. So we can think of this as, again, as a triangle. And we have an SU2 group element for each of the sides of the triangle. So those are the dots on the triangle and the lines that go through them. Then for the interaction, we want to take four triangles and glue them together to form a tetrahedron. And this implies a certain identification of different sides of these triangles. So for example, this side of this triangle must be identified with this side of this triangle when you want to combine all of these four triangles together to form a tetrahedron. And so by doing this identification, at the end, you'll end up with a closed tetrahedron like this. And so in these pictures here, I have these wires, and each wire corresponds to one of the three SU2 arguments in my field. And using this gives what's known as the Bulatov group field theory. And it has a trivial propagator. So the kinetic term is just the identity. And there's a non-local interaction based on the wiring that you see here, the way that these wires are identified. And this is explained in a very nice paper by Bulatov. And so for people who are interested in this, I really strongly recommend that they check out this paper. It's a very nice paper, very clearly written, and it goes through all of these steps. So again, you have this quadratic term, which will give you your propagator in the Feynman expansion, which will just be the identity because this is just phi squared. And then you have this interaction, which is phi to the fourth, and you have these identifications. So for example, this G1 and this G1 are the same. This G2 and this G2 are the same. This G3 and this G3 are the same. And this is essentially capturing the identification that you see here in this wiring. Okay, one thing that's worth pointing out is that I already mentioned this, but it may have passed quickly. This is non-local. So this interaction is non-local. And what do I mean by that? Well, a local interaction would be, let's say, phi to the fourth, where you'd have phi of G1, G2, G3, all that raised to the fourth power. Here, the arguments of each of the four phi fields are different. So in that sense, the interaction is non-local. But this is a very natural choice as soon as you understand that you have this geometric intuition behind it that tells you that you should identify different sides of the triangles when you glue them to form a tetrahedron. So from a geometric perspective, this is very natural. But from the quantum field theory perspective, where you're used to thinking of fields representing particles, then this is non-local. And so from a mathematical point of view, you have to be careful because now this is a little different. Okay. Now, as you're all aware, it's often very convenient to use a different representation. And so this is very much just like switching between positional momentum space and quantum field theory. And in this case, since we have SU2, we'll use the Wigner D matrices as a basis. So these are those matrices here. And we also have gauge invariants, so we have some intertwiners here. Now, the details here aren't so important. What's really important is just to keep in mind that because we're using this different representation, I can change between this phi field that depends on three SU2 arguments to this script phi field, which has three J labels and three M labels. And depending on the calculation I'm doing, one representation may be more convenient than the other.
There's a question in the chat.
Yes, please.
The question is, does the propagator correspond to any differential action?
Right. So what you can do is to add in a Laplacian here that acts on the SU2 group manifold. So that's something that you can do. In the Bulatov model, you don't have that. And that really just comes because you're trying to capture what the Spinfield model is telling you, which is that the edge amplitude is just one. So you can certainly include a differential operator. And in many group field theories, there will be one. But in this particular one, because you were trying to capture this geometric theory where the edge amplitude is 1, this choice is made where this is just the trivial one without any differential operator. But you can certainly include one if you like. But then this would be a different theory, of course. I hope that answers the question.
Yes, thanks.
Great. Okay, so again, what I was saying here is that we have a different representation which is available for group field theory. And so again, it's very much like switching between position, momentum space, and standard QFT. And so I don't want people to worry too much about the details here. And just to keep in mind that we can switch between this phi field here and this script phi here. And depending on the calculation that we're interested in doing, one representation may be more convenient than the other. So let's look at what the group field theory looks like in this new representation. So you can do some work. So really all you do is you start from this action here, and then you use this relation multiple times. And then you use the properties of these intertwiners and the Wigner D matrices. And this requires a fair bit of work, so that's why I'm not going through it here. And I've also ignored some signs. So some of the m's would have a minus sign in front of them, and there's an overall -1 to some power. For those of you who are interested in the details, I encourage you to take a look at Bulatov's paper. Everything is there. But the key thing that I want you to see is that if you use this new representation, you still have the kinetic term or the quadratic term, which of course will correspond to the propagator, which is still trivial. But then if you look at the interaction, you have this 6J symbol that has popped up. And this really comes from the properties of the intertwiners and the Wigner D matrices. And already now you can see that this is going to connect with the Ponzano Reggie model, where you had this vertex amplitude that depended on the 6J symbol. And so by using this new representation, the connection with the Ponzano Reggie spinfield model has all of a sudden become much, much clearer. Okay, so how do we recover Ponzano Reggie? Well, we have this partition function. So we just take this partition function. We have essentially the exponential of minus the GFT action. So this action that you see here. And we can expand that perturbatively, just following the standard Feynman procedure. So just take out your usual QFT textbook, follow exactly all of the same steps. And what you get is the following. You'll get a sum over the foams, and then a sum over all of the internal J labels. You have a face amplitude, and you have a vertex amplitude. And if you notice back here, I added in this lambda parameter here, or if you go back further, I put in this lambda parameter here to as a prefactor to the interaction term. So of course, that term comes along for the ride, and that shows up here. But if we set that equal to 1, then this is exactly the Ponzano Reggie spinfield model that we started with. So we can see that now we have a group field theory, the Bulatov GFT, that if you do a Feynman expansion, you recover the Ponzano Reggie spinfield model. And as I said earlier, this is a very useful thing to do because, okay, we do recover the spinfield model we started with, so that's very nice. So we can see that there's a nice connection between these approaches, but also the reformulation in terms of group field theory gives a lot of additional calculational tools that you just don't have when you only have a spinfield model. So depending on your calculation that you're interested in doing, perhaps the spinfield model is perfectly fine, and then you don't need the group field theory, and then that's great. But sometimes you may be interested in doing a calculation using a different approach, which doesn't rely on the spin foam expansion, or you could think of this as a sum of over Feynman diagrams. And then this reformulation in terms of group field theory can be very, very useful. Okay, let me say a little bit more about how the edge, vertex, and face amplitudes are recovered. I've already said it a little bit, but especially for the first 2 points, so I'll go quickly here. But the edge amplitude really just comes from the inverse of the kinetic or the quadratic term in the GFT action. So again, just like in standard QFT. And since this is a trivial quadratic term, that means that the edge amplitude will just be 1. So that's very straightforward. The vertex amplitude comes from the potential in the GFT action. And so this is just going to be a 4-valent interaction weighted by the 6J symbol as we saw. So once we rewrote the GFT action in terms of this representation in terms of the J and the M labels, then we see quite clearly that the vertex amplitude is going to be this 6J symbol. So that's where that comes from. And then finally, there's this extra face amplitude that I haven't talked about much. So I want to explain where that comes from. Now, because of the gauge invariance, both the edge amplitude and the vertex amplitude are independent of the M. But if we go back here, right, of course, we're summing over the M here, right? So you can see that this sum goes over not only the J labels, but also the M labels. So we have this sum over all of the M labels. But the edge amplitude and the vertex amplitude are independent of all of these M labels. So what that means is that if you have a given foam, then you have a sum over all of the MI that's possible, which just ends up being a prefactor because all of the other terms don't depend on M. So you can kind of take this sum over M out and just count how many M there are, and that gives you an overall prefactor. Now, if you think about this geometrically, each face in your spin foam has the same M, and it carries some label J. So when you sum over every M possible, you'll go from minus J up to plus J in steps of 1. And how many M's does that include? Well, that's 2J plus 1. So what that means is that for each face, this sum over M will contribute a multiplicative factor of dj. And so this is where this face amplitude comes from. It comes from just summing over the M labels in the theory. So let me just go back a little bit to where I made the comparison between the spin foam amplitude and the standard Feynman diagram. I can make this analogy a little bit clearer now. So the vertex amplitudes here match the vertex amplitudes here. These edge amplitudes really correspond to the propagators. The sum over J, of course, corresponds to sum over momenta, but here, these face amplitudes really correspond to the sum over M. So that can also be included in some way in the sum over momenta here. So these two terms combined essentially correspond to this sum over the internal momenta in this case. And then finally, you have the sum over the foams, which corresponds to the sum over the Feynman diagrams here. So the analogy here is essentially perfect. Okay, so that's where all of those terms come from. Let me stop here if there are any questions.
There's a question.
Yes, please.
It's very related to the first one. The question is why there are no derivative terms in the action. Maybe you can explain this again a little more.
Sure. So the reason for that really just comes from the Ponzano Reggie model. So sorry, let me go here. So when we have so this is the Ponzano Reggie model. This is the amplitude associated to it. And they give a very, very specific prescription of what the face, edge, and vertex amplitudes should be. So they say that the face amplitude should be 2j plus 1. They say that the edge amplitude should be 1, and that the vertex amplitude should be this 6j symbol. So now what I want to do is I want to construct a group field theory such that when I do, so I have a field, I have an action, and when I do a Feynman expansion of the partition function, then I want to recover this form here exactly. So I want to recover a very specific face amplitude, I want to recover a specific edge amplitude, and I want to recover a specific vertex amplitude. Okay, so, and in particular, I want to recover the edge amplitude to be 1. Okay, now the edges in a spin foam are essentially this edge here, and then there are 3 edges afterwards that leave the vertex. So there's one there, and then one here, and then a third one here. Now, each of these edges really corresponds to a node with 3 links going out of it and having that, evolve in time. And so it essentially, as you take this this node with the edges, the links that leave from it, sort of traces out this foam where the node traces out an edge and the links trace out a face. So what that means is that if I want to view my trivalent nodes here as particles, then their propagator will be this, corresponds to what this edge essentially. So I want their propagator to correspond to the edge amplitude. Now, since I want the propagator to give an edge amplitude which is just 1, that means I have to choose the quadratic term to just be trivial. So no derivative operator at all. Now, what I want to emphasize here is that this is a choice that's driven because I want to match Ponzano-Reggie. So now you could ask, okay, well, can I define a group field theory that has a derivative operator there? And the answer is yes, you can. And in fact, it's quite natural to do that. So you have a Laplacian on SU2, so you can use that as your derivative operator, and you can define a group field theory like that. So that's no problem. You can certainly do that. But then the question is, if you now expand that using the Feynman expansion, you will get a spin foam model. But is that spin foam model the Ponzano-Reggie one? And the answer to that is no. So you can certainly define a group field theory that has a derivative operator in it. There's no problem there. But here, just because I want to match Ponzano-Reggie, I've chosen the quadratic term to be trivial so that I get a propagator or an edge amplitude equal to 1. So that's a choice just to match Ponzano-Reggie, but that's not a choice that you're forced to do. You could choose something else. You could include a derivative operator. It's just that then in that case, you wouldn't match Ponzano-Reggie. So essentially, in terms of this representation, then you'd have a prefactor here that would depend on J, right? Because your derivative operator tells you about J. And again, this is perfectly well defined. It's a very good group field theory, but it won't match Ponzano-Reggie. Does that answer the question?
I think so.
Okay.
So in general, to summarize, so you could do derivative terms in the action that would be what you would be doing in the standard quantum field theory, but here you're not doing that because you want to get back the Ponzano-Reggie model, right?
Exactly.
Okay.
Exactly.
There is another question. It is in QFT, lambda is a coupling constant of interactions. How how to understand the lambda here?
In very much the same way. So this is some constant that shows up in the action, and it tells you how strong your interactions are. And you can make different choices here. Here, because I wanted to recover Ponzano Reggie, I just set lambda equals to 1. But in general, you can choose whatever value for lambda you would like.
Okay. So there are no more questions at the moment.
Okay. All right. So then let me continue then. Let's see, we were here. So essentially, this is how the various amplitudes are recovered, starting from the GFT action. Let me make a few comments. So when we look at Z, there are two sums in it, both over J and over all foams, and these both diverge for Ponzano Reggie. So if you want to use Ponzano Reggie, you have to somehow find a way to regulate those sums. Now, this isn't too surprising because in general, if you have an expansion Feynman diagrams, you usually expect it to at best be an asymptotic series. So this isn't super surprising. But let me just mention that if instead of looking at Ponzano Reggie, you look at Trivalent, and this is a spinfold model for, again, 3D Euclidean vacuum gravity, but now with a cosmological constant. So Ponzano Reggie assumes a vanishing cosmological constant. Trivalent is a spinfold model when you include a positive cosmological constant. Then what happens is that you replace the SU2 arguments in the GFT field by the quantum deformation of SU2. And then what this does is that it bounds the sum over J. So here, the sum over foams will still diverge, but in this case, at least the sum over J will now be bounded. Okay, but I don't want to go into this in too much detail. I just want you to be aware of this. Okay, a very important point is that the GFT field phi, this lives on the SU2, the tensor product of SU2, tensor product SU2, tensor product SU2, that has nothing to do with space or space-time. So the manifold that the GFT field lives on is not space or space-time. So of course in standard QFT it is, and this is an important distinction. The base manifold, or the manifold that the GFT field lives on, is not space or space-time at all. Rather, it's excitations of phi that correspond to quantum geometry. So if you have a number of excitations of this field and you glue them together, then this will give something that corresponds to a space-time. Okay, and finally, an important result is that for the spinfold models that we're interested in quantum gravity, there will exist a GFT such that if you take its partition function, expand it in a standard way, you recover the spinfold expansion. So if you're interested, I'll just refer you to this paper. Okay. Sorry, yeah, go ahead.
Related to the question about the lambda, there was the question if the coupling constant does affect the dynamics of the theory, and usually you have that the value of a coupling constant changes under renormalization, and if there's some physical significance in this, in this renormalization sense also in here.
Right. So I won't be talking about that very much. So I'll probably refer you to Valentin Bonzam's lectures. He'll talk about renormalization a little bit more. But let me just say that, yes, absolutely, we expect there to be renormalization here. And this is something that will play presumably an important role physically. So what you expect is that, again, you'll have some foams that you're summing over that will have some internal loops, and then you'll have this sum over the J's for these internal loops, and then you can perhaps make a distinction between the J's that are much larger than the J's on the boundary, and these would be quote unquote high energy modes that you could try to integrate out. So that's the basic picture. And we do expect that under this behavior, your coupling constants will run. The physical interpretation, I think, is not 100% clear to me yet. But there is a lot of work looking at this, at these, with this topic in general, and at these particular questions are part of that. So just to answer your question in short, yes, we expect there to be renormalization and the coupling constants will run. The interpretation of that, in terms of energy scales and things like that, isn't so clear to me.
Okay, thank you.
Yeah, no problem. Okay, right. So let me just repeat. So for quantum gravity, for spinfold models and quantum gravity, we can essentially always find a GFT that matches it. So that's a nice result. Okay. Now let me go and say just a few words about group field theory in general. So today, my goal really is just to make contact between quantum gravity and group field theory and to show you what the link is. So I'm really focusing on that particular aspect of group field theory. But group field theory is much more general, right? So in the same way that quantum field theory is much more general than just QED, group field theory is much more general than just, some models for quantum gravity. So there are group field theories that correspond to many quantum gravity theories. So for example, so far we've been looking at 3D Euclidean gravity, but we also have GFTs that correspond to 4D Lorentzian gravity, which we'll look at next. And also to other versions as well, with or without a cosmological constant, in vacuum or with some matter fields. These are all models that can be captured by group field theories. And also there are group field theories that don't correspond to a theory of quantum gravity at all. So of course you can define a field theory. You give some action for some field where you have some group which is mapped to, let's say, the complex numbers. And typically you're interested in a Lie group, but you could even go beyond that if you really want. So I want you to keep in mind that group field theories are very, very general. So far, and also going on, I'm really going to focus on group field theories that are relevant for quantum gravity. And this will lead me to make certain choices. So for example, for Ponzano Reggie, I made the choice that the edge amplitude would just be 1, right? And that was to match Ponzano Reggie, and that led us to a very specific group field theory. But you can certainly define a group field theory that includes a kinetic term, and then this group field theory will describe something else. So group field theories are extremely general, and that's an important point to keep in mind. But again, for what I'll be talking about in this mini class, I'm really just going to focus on the connection to quantum gravity. And so I'll be making specific choices in the forms of group field theories that I look at, motivated by those choices. But you should keep in mind that you can do something much more general. Okay, so let's go on now. I've spoken so far about 3-dimensional Euclidean quantum gravity. Now let's go on and look at the 4-dimensional Lorentzian case. Okay, now this can be quite rich. And so for the sake of simplicity, I'm just going to focus on loop quantum gravity, which is based on a simplicial complex. So you can think of this as, let's say if you have a 2-dimensional surface, you can view it as we did for Ponzano Reggie as just breaking it up into all these triangles. But in principle, your 2D surface, you could also include, rectangles or pentagons or hexagons, and have a combination of triangles and all of the other polyhedra. But to keep things simple, we just said, okay, let's just keep, describe our 2-dimensional surface in terms of triangles. And then we were looking at the 3-dimensional space. We only considered a 3D simplicial complex, So we were looking at this 3D discretized in terms of tetrahedra. Of course, you could have added in cubes or things more complicated than that also. But just for simplicity, we stuck with the simplest case. And that's what we'll do here again. So I want to look at four-dimensional Lorentzian vacuum quantum gravity based on a simplicial complex. So what does that mean? That means that for boundary states, we'll only consider spin networks whose graphs are dual to a simplicial 3 complex. What does this mean? This means that we're looking at spin networks that correspond to a triangulation, or if you prefer, they're dual to tetrahedra. And so if you have a graph which is dual to a bunch of tetrahedra glued to each other, then each of your nodes will have 4 links leaving it. So of course, a tetrahedron has 4 faces. So you have the node that lives in the middle of the tetrahedron, and then you have 4 links, and each of those 4 links passes through one face of your tetrahedron. Okay, so that's tells you about the restriction on the boundary states. And for the bulk, we'll only consider foams that are dual to a simplicial 4 complex. So this is very much the same thing that we did in the 3-dimensional case, where we asked that the foams be dual to a simplicial 3 complex. Now we're looking at it in 4 dimensions, so we're looking at foams that are dual to a simplicial 4 complex. So what this means is that all the vertices in the spin foam model will be 5-valent, and that at each edge in the spin foam, there are 4 faces that meet at that edge, and that just comes from the fact that the nodes are 4-valent. So that's exactly the same information. Now, again, I'm doing this for the sake of simplicity. It is possible to consider the general case, and so I'll refer you to this paper if you're interested. But already, even a group field theory that generates, in quotation marks, only this type of graphs is already very, very rich. So this already tells us a lot about the theory. And of course, we can go beyond that, but for today, I'm really going to stop here.
There's
okay.
a question.
Yes, go ahead.
The question is there any 2D GFT which is not a matrix model?
So of course, the simplest one is a matrix model. Matrix models correspond to vacuum gravity. So if you want to add in matter fields, then you need to add extra information, and then you would get a GFT that would look like a matrix model, except with some extra arguments corresponding to the matter field.
Okay, thank you.
Yeah. And there may be some other possibilities too. So for example, if you're interested in a higher curvature theory, then there may be some possibilities. I'm not sure about that though. But you can certainly define a GFT that would correspond to something 2-dimensional, but the interpretation may not be so easy. But if you're just interested in coupling matter to 2-dimensional gravity, then that is certainly possible.
Thanks.
Okay, great. Okay, so again, so what we'll do is we'll start from a spin foam model and then see what group field theory we can construct that will give the same transition amplitude. So for 4D Lorentzian vacuum quantum gravity, we'll use the EPRL spin foam model, which is given here. And again, you have the sum over foams, you have the sum over the internal quantum numbers. So here you have the J's on the faces and the intertwiners iota on the edges. And you have a face amplitude and a vertex amplitude. You also have an edge amplitude, but again, this will just be 1. Okay, and as I said, this sum the sum over foams is over all foams that are dual to simplicial complexes that interpolate between the initial and final spin networks. Okay, so as I said, the edge amplitude is just 1, so that's why it's not shown there. The face amplitude, again, is exactly the same. It's just 2J plus 1. And then the vertex amplitude is quite complicated. I won't give any details here, but it's a 15J symbol, which is constructed from the various labels of the edges that meet at the vertex. So here you'll have 5 edges that meet at a vertex. And so each edge will carry an intertwiner. And you'll have 10 faces that also meet at the vertex, and they each carry a spin j. And so from these quantities, you can construct a 15J symbol, and that is the vertex amplitude. Okay, so for details, I'll just refer you to the paper on the spinfold model. Now, the general structure of the vertex can be described in the following graphical way. And this is very similar to what I showed earlier for the Ponzano Reggie model, where you had these triangles that you glued together to form a tetrahedron by identifying certain sides of the triangle. Here it's very much the same thing. You have these 5 tetrahedra that you want to glue together in such a way to form a 4 simplex. And this is done by gluing the surfaces of the tetrahedra in a certain way. And that's shown in the identification of the wiring here. Okay, and here each of these wires carries a spin quantum number j. And then the box here, this carries the intertwiner iota label. And so you can quickly count that you have 5 intertwiners, you have 10 j's, and combine that all together, you can calculate a 15J symbol, which will be your vertex amplitude. Now, geometrically, one way to think about this is that each tetrahedron carries an intertwiner, and together with the J's, that tells you what its volume is, and 4 spins. And each spin tells you about the area of one of the triangles forming the surface of the tetrahedron. Okay, so this is the vertex that you have there. Now, we've already seen how this works in the 3D case, so now I'll go a little bit faster. So again, it's very natural to interpret these spinfold amplitudes as a sum of Feynman diagrams for geometric particles. And now, of course, the particles will be these quanta of 3D geometry corresponding to tetrahedra. So we have these particles, as I said, that correspond to tetrahedra. So these are geometric particles, geometric excitations. Again, their propagators are trivial because these tetrahedra travel along the edges, and the edge amplitude is just 1. So what that means is that the propagator is trivial. And the interaction occurs at the vertices, where you have these 5 tetrahedra that meet to form a 4 simplex, which was shown graphically in this figure here with the wiring showing the identifications between the different J labels. Okay, so what this means is that now we should introduce a field. So if we want to have a group field theory that captures this spinfold model, now we want to introduce a different field. These particles now carry 4 J or 4 SU2 arguments. So now we have a GFT field that has 4 SU2 arguments. And each argument corresponds to one surface of the tetrahedron. Right? So the area, it tells you about the area of one triangle on the surface of the tetrahedron. Okay. Now, of course, we want our group field theory to match the amplitudes of the EPRL spinfold model. And so we need a kinetic term in the action, and this will be trivial just because the edge amplitude is 1. So again, exactly the same thing as before. It is possible to include a kinetic, a derivative operator if you like, but here, because we're motivated by the EPRL spinfold model, we choose a kinetic term knowing in advance that we need to choose it to match the edge amplitude, which is just 1. So we choose a quadratic term, which is just trivial, just trivial. And the potential in the action, in the GFT action, will be of the order of phi to the 5th, because you have 5 tetrahedra that meet at a spin film vertex. Okay.
There's another question.
Yes, please.
Why is the field now complex while it was real in the 3D case?
Right. So here, here I'm making this choice because I'm already thinking about making contact with canonical quantum gravity later. You could choose to make the Bulatov model have phi being a map to the complex numbers also. And here I'm making this choice because I want to be able to introduce in the quantum theory operators corresponding to phi and phi dagger. So that's why I have this in mind here. But you could do the same thing in the Bulatov model if you like.
Okay, thank you.
Yeah, no problem. Okay. Now, as before, we have a gauge invariance. Geometrically, this corresponds to asking that all of the triangles close so that you have a tetrahedra, which doesn't have any gaps anywhere, right? All the triangles match perfectly to form the tetrahedron. And this gauge invariance, we want to encode that in the Gft field phi also. And again, it's the same thing. We just ask that if we multiply on the right all of the 4 arguments by the same group element, that the value of phi doesn't change. Okay. And again, it's always very useful to express the Gft field in another representation. So again, depending on the calculation, one representation may be more useful than another. So I'll do very much the same thing as before. I'll use the Wigner D matrices here, and I'll use the intertwiners here to transform between this phi representation and this script phi representation. The main difference now is that you have this extra intertwiner label here. I should mention that here, these are the 2 representations that I've been discussing in this mini class, but they're not the only ones, of course, right? There are many representations that are possible, and depending on the calculation that you're interested in, one may be more useful than the other. For what I'm talking about here, these are the 2 representations that are most useful, but they're by no means the only ones. So if you're interested in doing something else beyond what I cover in these lectures, then it's certainly possible that a completely different representation may be useful also. So these are 2 of them, but they're not. It's not, you know, there are more than just these 2. Okay. So the key thing here again is that I can express my Gft field in terms of this quantity or in terms of this quantity here, one or the other. And finally, this quantity is quite long and takes up a lot of space when we write it out every time. So a shorthand notation is convenient, and I'll just put these little vectors over the J and the M labels here. And then that's just some shorthand notation. So
there's another question.
Yes.
Again, about the field being complex. The question, does this relate to the Lorentzian spacetime? No, it doesn't. No. I'll say a little bit more about this later. It really has to do with the fact that I want to introduce operators, and I'll be doing this later, corresponding to the field phi and its complex conjugate. Okay.
And I want these to be different operators. So this would not be possible if it was mapped to the real case. So it's more to do with that. And I think this will become clearer in maybe 10 or 15 minutes when I get there.
Okay, thank you.
Yeah. Okay. So this is the GFT field that I have, the next step is to ask what is its action. And again, I choose the action by mapping to the spinfold amplitude and comparing the edge amplitude with the propagator and the vertex amplitude with the interaction term. Okay, so here I've given a general form. So I have this quadratic term here, which will tell me about my propagator. And then I have this potential term here, where I have a product of 5 fields. And here I have the field, I have its complex conjugate, and I also have this dot, dot, dot here, because I could also have, let's say, so I can think of this as phi cubed, this is phi bar cubed. I could also have phi times phi bar to the 4th. I could have phi squared, phi bar cubed, and so on. And the key thing is that the quadratic terms will determine the propagator, and the quintic terms will determine the interaction when I do the Finemen expansion. Now, the action is real if I choose this kinetic term here, script k here, to be real. So that's what we'll do. And as I already mentioned, here I looked at, I've included 2 terms in the potential, but here I have this phi to the 5th, phi bar to the 5th. I can also have other terms, let's say phi bar 4th phi, or phi bar phi to the 4th, and so on. All of these other mixed terms between phi and phi bar, such that the total power is 5. Okay. Now, for the wiring that we have in the EPRL model, the kinetic term is just diagonal. And so you have, and what that means is that you get these Kronecker deltas between the J labels, the M labels, and the iota labels. Here I've left a possible dependence on J here, and in principle it could also depend on iota. But J would be especially relevant if you're interested in adding in a Laplacian, so some derivative operator. Now, for vacuum EPRL, if we want to match, then we just choose this little k to be equal to 1. What we'll see later, when we go on to talk about cosmology, we'll have to add in matter. And then if we add in matter, then this little k here will no longer be 1. It'll be a little bit more complicated. It'll know about the matter field. Okay, but the key thing here is to notice that for EPRL, the kinetic term just has all of these Kronecker deltas in it. Okay, then the potential is again non-local because you're identifying different arguments in the phi terms so that you can glue all of these 5 tetrahedra together to make a 4 simplex. So this is exactly analogous to what happened in the 3D case where you wanted to make these identifications so you could glue the triangles together to form a tetrahedron. So this is exactly the same thing except 1 dimension up. And here I've shown the identification. So for example, you have this J1 here, which then is identified with this J1 here, right? And you have this J4 here, which is identified with this J4 here, and so on. And so you have these 5 phi terms that are all that show up in the potential, and then you have some weighting here, and the weighting is just the 15J symbol, right? Because we want to match the EPRL spinfold model, so that means that the weighting of my GFT field in this representation should be the 15J symbol. So that's how we choose that. Okay. And here I should mention that this is just the first term. So this is the term that is phi to the 5th. You can do something very similar for phi bar to the 5th and mixed terms also. So I won't show all of that. It's very much the same thing. Okay, so this then is all that I wanted to say about the connection to spinfold models. So we started with a spinfold model, and we found what the edge amplitude was, what the vertex amplitude was, what the face amplitude was, and from that we were able to construct this GFT model with this action And for a certain choice of this script K and of the potential here, we get a GFT that when you do the perturbative expansion of its partition function, you'll recover the EPRL spinful model. So I won't go through the steps here because they're very, very similar. Everything's exactly the same. The kinetic term is mapped to the edge amplitude. The potential is mapped to the vertex amplitude, and the face amplitude is given just by this sum over the M labels, which are free. Okay, so that's the connection coming from the spinful model to the group field theory. And what I want to do for the remainder is to talk about the connection with canonical loop quantum gravity. And this is where the reason for having this phi field being complex will become important. Okay, so as I said, this group field theory, which I've just described to you, so a certain definition of the field and a certain choice of the action, has been constructed so the perturbative expansion of its partition function gives the EPRL spinful model. So that's what I already said. Now, it's also possible to make contact with canonical loop quantum gravity. And we can do this by considering a Fock-like quantization of the GFT with creation and annihilation operators. So, of course, when you have a standard quantum field theory, then you can either calculate things using the path integral, or you can use the canonical framework. So here we'd like to do the same thing. I've been talking a lot about the path integral approach, but we can also do a sort of canonical quantization of the GFT. So let me explain how that's done in this context. So we have creation operators, which will create these geometric excitations. So think of them as a creation operator corresponding to a tetrahedron carrying some quantum numbers, J1, J2, J3, J4, telling you about the areas of the triangles forming the tetrahedron, and then the intertwiner. And then that will create one tetrahedron. And then if you want to glue several of them together to form a larger three-dimensional space, then these tetrahedra, or these nodes, can be glued together through entanglement. So let me say a little bit more about this. Okay, so the first step that we have to do is to define some GFT field operators. So an operator corresponding to the field phi and an operator corresponding to the field phi dagger. And this is the reason why I wanted my GFT field to be complex. It's because I wanted to be able to define these two operators and to not have them be the same. So of course, if you had the GFT field being real, then you wouldn't have two independent operators like this. But because our GFT field is complex, now we have these two independent operators, phi and phi dagger. And that's very important because we want one of them to correspond to a creation operator and one to correspond to an annihilation operator. So for that, we impose these commutation relations. So we define these operators and we require that they satisfy these commutation relations. So this is very much the commutation relations that you would have for creation and annihilation operators in standard QFT. And finally, we define the Fock vacuum, and that's the state which is annihilated by all of the phi operators, no matter the indices.
Here you assume that the fields are bosonic, right?
Yes. So here we are assuming that the fields are bosonic, and that's something which is put in by hand in this case. So that's a choice that's made. Yeah.
Okay.
Okay. Now, I don't want to go into this in much detail. I just want to mention that, the GFT framework is timeless, right? There's no time variable there. So what that means is that these operators are timeless. And what that means is that in quantum gravity, we have the problem of time that has to be addressed somehow. And so this problem arises in group field theory also. And so when working in this approach, you have to think about the same types of problems, of course, that you have in other approaches. So it's not, by working in group field theory, you get a new framework that gives you some new calculational tools, but a lot of the conceptual issues that you have to address are still there. So here, the problem of time is still present. One possible solution is to use relational observables, and so I'll talk about that when I talk about cosmology. But I just want to mention that the problem of time is still here, and you still have to address it. And just as an aside, I won't go into this in much detail, but if your field phi is defined on some group manifold, and you can single out part of your group manifold as being the real line, then it might be possible that you could use that part of the group as a time direction. And then if you have that, you might be able to derive some equal time commutation relations for the group field theory. And so this has been done in some cases, and so I'll refer you to those papers. But in general, you have to work in this timeless framework. Okay.
Two
sorry.
Questions on the bosonic commutation relations. The one is, has anybody looked in fermionic quantization? And the other one is if there's a specific motivation for doing bosonic quantization, or is it just for simplicity? Right.
So let me start with the second question first. There is a motivation for using bosonic commutation relations, and the reason for that is that, and again, this is some input, so it's not set in stone, but the idea is that we would expect there to be possible that two quanta of geometry, two tetrahedra, be identical. And of course, if it's fermionic, then that's not possible. And remember that when you create, let's say a spatial slice using these operators, you'll have many quanta of geometry, and then you connect them through entanglement. But if it's bosonic, then it's possible to have one quantum of geometry over here and another quantum of geometry over here that have the same quantum numbers. If it's fermionic, then that's not possible. So for that reason, it just seems more natural that you could have different quanta of geometry, possibly quite far separated once you figure out the connectivity between them, that are identical. And so for that reason, people usually work with the bosonic case. Now, that said, you could certainly consider the fermionic case also. So you could just put in by hand and ask, I want these to be Grassmannian variables, and what happens then? And I think that would be interesting to explore, but I don't think anyone has done that yet, at least not as far as I know.
Okay, thank you.
Okay, great. Okay, so we have these operators, and we want to associate one with creation, one with annihilation. And so, of course, because the Fock vacuum is annihilated by phi, that means that phi is annihilation and phi dagger will be creation. So these creation operators, what do? They create disjointed parts of a spin network. So for example, if I act with two creation operators with different quantum numbers like this, I get these two disconnected nodes. So I have these two excitations, right? I have one node here, I have another node here, and they don't really talk to each other. Okay, and right, so let me just go through this slowly. So I have one creation operator here with all of these quantum numbers, and then this other intertwiner quantum number. And so that will correspond to this node here. So I have this 4-valent node with all of these J's and M's and an intertwiner. And then this creation operator here corresponds to this disconnected node. Okay, so this is what happens when you just act with a creation operator. Now, what happens if you want to start connecting them? Oh, and I should mention that the Fock vacuum here is just the no space state. So in that case, there's just no nodes at all.
That being said, there's another question.
Yep.
Since we consider interactions here, can we still construct the Fock vacuum?
Right, so this is just a construction. Now, the question that you're asking, I think, is this in some sense a minimum of, let's say, some energy functional, something like that. And so is this a state that we want to expand around? And the answer to that is not necessarily. So this right now, I want to present just as a mathematical construction. And then later you can ask, okay, well, is this really a vacuum state around which you want to do a perturbative expansion to study physics that we're interested in? And for that, I think the answer is no, at least not in general. But still, this will give us a way to define the theory.
Okay, thanks.
Great. Okay, so these are two nodes that we create in this way. And now we want to start connecting them. So let's say I create a whole bunch of nodes and I want to connect them so that I have something that looks like a spin network. What does that look like? Now, the links, we can just connect them by entangling in the M labels. And the way that this entanglement is done is so that the total angular momentum is just 0. And of course, this is only possible if the J quantum numbers agree. So you know just from quantum mechanics that when you want to add angular momentum together, if you want to get 0, your two J labels have to be equal to each other. So the same thing is true here. So here's an example. What I do is I have these two creation operators, but now I have some entanglement between these quantum numbers here and these quantum numbers here. And this entanglement is such that the total spin is equal to 0. So if you just ignore all of the other quantum numbers elsewhere, you'll see that this is just the singlet state for J equals to 1/2. And so what that means is that now I've connected these two nodes along this link like this. So by doing this entanglement, I only have this J label that's left, which is equal to 1/2. And then of course, the other nodes, which I haven't touched, are still there. But I could also entangle them with other links also. So this is how we start to glue together these different nodes to get something which is connected. Okay, so more generally, let me explain the general procedure and I'll refer you to this paper for details. You want to act with creation operators for each node. So let's say you want a spin network that has 10 nodes, then you have 10 creation operators. And these have to carry, of course, the appropriate J and iota quantum numbers. Then you connect links through entanglement of the M labels in such a way so that the total angular momentum along that connected link is 0. And so for each pair, you'll get an operator that looks a little bit like this. And here I'm just suppressing all of the other labels just to keep things simple. But this really is just the linear combination so that the total angular momentum is 0. So of course, this gives you some entanglement in M. And it's this entanglement that glues these two links together. Okay. And of course, this is a sum that's just for one link that is being glued together. There will be many different links, of course, throughout the whole spin network. So there'll be sums of this type repeated many, many times, one for each of the links that will be created. As an aside, let me just mention that I think there's a very interesting relationship between the connectivity and entanglement that we have here. So we find that by imposing that these two disjoint links be entangled ends up connecting them. So there's a relationship between entanglement and connectivity. And it turns out that this is very similar to what happens in some proposals in the ADS-CFT correspondence. So I won't go into details here, but I just want to mention that because I think there are possibly some very, very interesting connections to be made there. Okay, so now I've made a connection between group field theory and spin networks. So you can think of that essentially as being the boundary states. And so now what about dynamics? So how do I make connection between group field theory and the dynamics of canonical loop quantum gravity? And of course, in canonical loop quantum gravity, you're interested in the inner product, and not just any inner product, but the physical inner product between an initial and a final state. And this physical inner product is obtained by acting with the projector on your states and then taking the inner product. And this projector onto the physical Hilbert space is essentially requiring that the Hamiltonian constraint operator gives 0. So you're asking that this delta function of the Hamiltonian constraint operator, that you only want support where CH is equal to 0. And so you can expand it in this way. Now, the reason why I put this, this symbol here rather than equality is, of course, a delta function is distributional. And so you have to be careful about how you define this in, in mathematical terms. So you get something at the end, which is a number and not a distribution. So you do have to be a little bit careful with this, but the basic idea is that your projector is onto the set of states that are annihilated by the Hamiltonian constraint operator. So this is what happens in canonical loop quantum gravity. You want to be able to calculate inner products like this. Now, if you have some boundary state in GFT, which corresponds to a spin network, so you can relate the GFT states to spin networks, then you can calculate the transition amplitude within the context of group field theory. And you can compare that to the physical inner product. And it really should match. So the GFT partition function, or equivalently its action, implicitly defines a Hamiltonian constraint operator. So this partition function is very closely related to this projector, which is constructed from the constraint operator, the Hamiltonian constraint operator. Okay, now again, to make the equality exact here, you have to be careful because these quantities can be distributional, but this is essentially what you want to do. And so you can relate the full dynamics in canonical loop quantum gravity to group field theory also. So there's a connection not only between spin foams, but also with canonical loop quantum gravity. Okay, so nonetheless, despite these connections, there are some differences which I think are important. And I want to emphasize what these distinctions are. So first, in canonical loop quantum gravity, when you talk about a spin network, this is a graph with all of the J and iota labels on it, but this graph is embedded in a manifold. So for example, you can ask whether the graph loops around itself or not. Are there any knots in the graph? Now, on the other hand, in group field theory, when you connect these different nodes through entanglement, this really generates an abstract graph. So there's no sense in which you can ask whether there are any knots or any braiding in this abstract graph of GFT. So that's one important distinction between the two theories. Also, in canonical loop quantum gravity, you have this cylindrical consistency in spin networks. So what that means is that you can always add new links with j equals 0 or remove links with j is equal to 0, and you get exactly the same state. This isn't possible in group field theory, and the reason for that is that you have these creation and annihilation operators. And so from them, for example, you can construct a number operator. And you could create a number operator with j is equal to 0. And so by acting on your state, you will know how many quantum geometry you have with j is equal to 0. And that means you can't just take them away and keep the same state. There are some operators within group field theory which are sensitive to the presence or absence of links with j is equal to 0. So that's another difference between the two theories. Also, in group field theory, you have these bosonic statistics, and this implies that there's a sort of permutation symmetry between the nodes in your spin network. Right? So essentially, you have these bosonic degrees of freedom, so they're indistinguishable, and so that means that you can permute the labels on your spin network. In canonical loop quantum gravity, again, because your graph is embedded, these nodes are typically distinguishable, and so you can't really permute labels like that. And finally, again, because the GFT quanta are indistinguishable, the inner product between different graphs can be different. So these are some differences with canonical loop quantum gravity. So it's very close, but there are some differences at a technical level that people should be aware of. Okay, so I'm almost done. So I'll summarize here. So group field theory is just a field theory that lives on a group manifold. I've been especially interested in discussing the group field theories that are linked to quantum gravity. And so that leads us to consider a certain type of group field theory. But of course, group field theories are much more general than just the ones that we use for quantum gravity. And for the group field theories that are related to quantum gravity, we can understand their partition function when we do a perturbative expansion of it is the same as what you have in a certain spinful model. So if we're interested in loop quantum gravity, so Lorentzian four-dimensional vacuum quantum gravity, if we're interested in the simplicial case, then we're looking at 4 valent spin networks, and the GFT field has 4 SU2 arguments. And then the last thing that I discussed was the canonical quantization by introducing these creation and annihilation operators. And then these particles are these quanta of geometry that you can think of as tetrahedra or these spin network nodes. And these can be connected by entangling them. The next steps, so I want to discuss condensate cosmology next. I'll see how many questions there are. I may say a few words about that at the end of today, or if there are a lot of questions, then I can wait until Thursday. And then also to talk about tensor modes, the more field theoretic aspects of group field theory, including renormalization. These last topics will be covered by Valentin Bozon. Okay, so of course there are many, many references on group field theory. Here I've selected 4 of them that discuss the foundations of group field theory, which I think may be useful. So I think these are a good starting point, but of course there are many more than this. So I'll stop here for questions.
Okay, thank you for this nice first lecture. Then let's collect some questions. So please write in the chat or raise your hand for questions. So in principle, we're very good in time. So also if you want to.
We have time, and also if there aren't any questions, I'm happy to just start on cosmology and take maybe 10 minutes for that. But I can also wait until later if there are many questions. So it's whatever works best.
At the moment, it does not seem to be many questions. Or a lot of questions during your talk.
Right, and that was good. So, but
yes, I have maybe a little bit a naive question.
Sure.
Would it be possible to have try to make this well defined, but like the time evolution operator is somehow also a group element. So could you imagine that this is part of the group manifold you're quantizing over?
Right. So this this is what I mentioned very briefly here at the bottom. So if your group manifold does have, if you can split it into, say, some subgroup cross R, then in some cases you can use R as the time direction. So for example, the example that's considered in these 2 papers is when you couple group field theory like we saw here to a massless scalar field. Mm-hmm. And then this massless scalar field you can use as a clock. I mean, this is often done in quantum cosmology. Right. And it turns out to be possible here also. And so then you can kind of single out this scalar field degree of freedom as your time direction. And then you can derive these equal time commutation relations, and then you really have an evolution operator. right? So when you have a time coordinate, you can often think of, okay, I can view my evolution as evolution in time,
Right.
and then this becomes possible in this case.
Okay, thank you.
Yeah. So in general, you're in a timeless framework, and you can't really think of it as evolution in time. You really have to think in terms of transition amplitudes and address the problem of time in some way, which may not be very easy. But in this particular case where you have a massive scalar field, then things become much easier.
Okay, I see. There's still no further questions. Let's maybe last call for questions. Let's wait some more moments.
Sure.
Yeah. But yeah, it doesn't seem to be any more questions. So if you want to say any, no, there's a last question.
Okay.
There is a question. The powers of the interaction in both the examples considered today have been chosen in a way to match GFT to Ponzano, Reggie, or LQG. Can this be generalized to include higher order powers, or is that non-physical? Also, can you explain why there is an effort being made to connect GFT with theories like LQG?
Right. So you can certainly include other types of interactions. I mean, there's no problem whatsoever in doing that. And so if I just go back here, right? I mean, group field theories in general is very large, and you can consider all kinds of interactions in that case. So you can certainly consider, let's say, phi to the 6, phi to the 7, whatever type of interaction you might be interested in is possible. As I was saying, and as the question states, I mean, here I've made specific choices motivated to match with LQG or with Ponzano Reggie. Now, the other question, why are we interested in this matching? Well, I'm coming from the perspective of someone who works on quantum gravity. And so I'm interested in tools that can allow me to do calculations within quantum gravity that may be more powerful than what is already there. So as I've said, spin foam models can be very useful, but for some types of calculations, they're not the best tool. So it's just like in standard quantum field theory. In some cases, you can do calculations using Feynman diagrams and it works extremely well. In other cases, it doesn't. And by introducing a group field theory, we get new tools that we can use to do certain types of calculations in a much more powerful way than what was available before. So of course, there are still calculations where spin foam amplitudes are the way to go. But now for some other types of calculations, and I'll talk about one case in cosmology, you have all of these tools coming from the field theory that make calculations much simpler. So coming from the perspective of quantum gravity, I view group field theory as a very powerful tool to do some calculations. For someone who's more interested in group field theory as a standalone object, then they may not be particularly interested in quantum gravity, and then they may not be particularly interested in the specific group field theories that I discussed today. So if you're interested in that as a mathematical object or as an object that describes something else, then you may be interested in different types of group field theory. But at least from the quantum gravity perspective, I think these are particular group field theories that are quite interesting. They're not the only ones. I mean, here, of course, in 2 hours, I don't have time to talk about all of the versions of group field theory that are relevant for quantum gravity. So I don't want people to think that these are the only 2 group field theories that are relevant for quantum gravity. There are others, but these are perhaps first steps in that direction.
Okay, thank you. Do you know about other applications of group field theory in other fields of physics?
Right. So I'm not an expert on this, but I know that tensor models, which are very closely related to group field theory, and I think Valentin will say a little bit more about this in his lectures. They've been used a lot in the SYK model in essentially 2-dimensional condensed matter. physics. I don't know the details, but I know they've been used there a lot.
Okay, thanks. Are there other questions? Okay, this seems not to be the case. So in principle, there are 13 more minutes according to our official schedule. So if you want to say any more,
well, let me 13 minutes. Why don't I start on cosmology, condensate cosmology, and I can go slowly, and then I'll repeat the same information at the beginning on Thursday, but maybe go a little bit faster. Does that seem okay?
Sounds reasonable.
Okay, so let me just stop sharing that. Okay, do you see this?
Yes.
Okay, great. So the first part of what I was discussing was really, group field theory. What is it? How is it related to quantum gravity? And I was looking a lot at the connections between starting from a spinfold model, getting a group field theory, and then also relating group field theory to canonical loop quantum gravity at the end. And so a lot of this, the focus was on, going back and forth between these different frameworks and understanding how they're related to each other. But as I've said, one of the main points behind group field theory is to get these new tools to calculate things that would be much harder to calculate in a different context. And so here I want to give one example where the group field theory framework is very powerful to do certain types of calculations. And what's nice is that these are calculations that are very relevant for what we're interested in studying, one of which is cosmology. So again, I won't get very far, and I'll do this again on Thursday, but just to remind you, I'm sure everyone is already aware of this, but one of the best chances that we have to test quantum gravity is in the early universe. So we certainly expect that when the space-time curvature becomes really large, like we think it was in the very early universe, then quantum gravity effects would become important. And it's quite possible that these early quantum gravity effects could then leave an imprint on what we see in the cosmic microwave background today. So there's been a lot of work in loop quantum cosmology in this direction, but it's really based on starting from GR, imposing symmetries first, so homogeneity and isotropy, and then you get this very simple symmetric model, and you quantize that. And so that's how loop quantum cosmology works. I believe you've already heard a little bit about that. And this has been very powerful, and we've learned a lot from this. And I've worked on this a lot myself. And as I said, we've learned a lot, and we're still learning. So I think this is a very productive path to follow. But it's clear that it'd be even better if we could start from full quantum gravity and then study its cosmological sector. So in loop quantum cosmology, you take the classical theory, you simplify it, and then you quantize the simpler theory. But if we could start from the full quantum gravity and then study the part of that theory that corresponds to cosmology, that would be even better. Okay. Now, if geometry is quantized, which is what loop quantum gravity predicts, right, you have this discrete spectrum for the area operator and for the volume operator and so on, then it's reasonable to expect that our universe is made of a huge number of quanta of geometry, right? So if I look at, let's say, this region here, which is maybe, 100 cubic centimeters or something like that, then this, I would expect, would be composed of a humongous number of quanta of geometry that each have, a Planck volume, each contribute a Planckian volume. And so what that means, coming from the perspective of group field theory, is that we're interested in states that are highly excited. And when I say highly excited, I mean have many quanta of geometry. And specifically, we'll look at condensate states, and I'll justify that a little bit more later. And also, we're interested in their collective behavior. So we're interested in the emergent dynamics that we can look at when we have these collective observables. And I want to make a parallel here with hydrodynamics. So if we're interested in studying how a river is flowing, we don't zoom down to a specific water molecule and say, okay, what specific quantum state is this water molecule in? Rather, we're interested in how the large number of molecules all behave collectively. And so that's what we want to do here too. We want to focus on the collective behavior of a large number of quanta in group field theory. And so what I'll cover in more detail on Thursday is first, I'll explain how we can add matter to group field theory, in this case, a scalar field. And this, of course, is necessary to study cosmology. So as you know, if you have a Friedmann universe in classical GR, you need to couple some matter to it to have some dynamics. Otherwise, you just get Minkowski space. So we really need to include some matter. Then I'll explain a little bit more why we're interested in condensate states and define what I mean in detail with that. And then we can see the cosmological dynamics that emerge. Okay, so as I already said, if we're interested in cosmology, we have to include a matter field. And I'll say a little bit about how to include a matter field, and then I'll stop, and then we can continue on Thursday. So for simplicity, what I'll do is I'll just add a massless scalar field, and I'll denote the scalar field by chi. Of course, we could do things that are more general or more complicated, but I want to do the simple thing first, and then afterwards we can come back and consider more complicated cases. So what happens to handle this in group field theory is that now we have these quanta of geometry that are no longer empty. So before we were thinking of vacuum quantum gravity, now we have a scalar field. So now our tetrahedron is no longer vacuum, but it carries some amount of matter with it. So what that means is that our Gft field has an extra argument corresponding to the scalar field. And if we look at the operators in the canonical version of Gft, so the phi and phi dagger operators, these operators are extended in the same way. So we add an extra chi label to these operators. Okay, and then finally, we change the Gft action so that we have a scalar field that's also present, again, with my scalar field is chi. And here I've suppressed all of the SU2 quantum numbers, just so you can see the dependence on the scalar field, but the combinatorics that we saw just before are exactly the same. So nothing changes there. It's just that now we have these fields that depend on chi1 and chi2 in the quadratic term. And we have this weighting here that'll depend on the difference squared. And then in the interactions, we have that all of the fields are evaluated at the same value of chi. So if you remember, in terms of the SU2 variables, the Gft interaction is non-local, but it is local in terms of the matter field. So that's a difference. And this particular choice comes from localizing the scalar field on vertices in the Spinfield model. So of course we have a scalar field, so the natural place to localize chi in a Spinfield model is on these zero-dimensional objects, which are vertices. So if you have a vertex here, has some value chi, let's say chi1, you have another vertex here, it has some value chi2. So that means that if you have an edge that goes between these two vertices, you expect the value of chi to possibly change as it propagates. So that's why in this quadratic or the kinetic term, we have different values for chi. We have chi1 and chi2. And similarly, if at a vertex you have a fixed value of chi, that means that all of the fields that arrive there have the same value of chi where they meet. So that's why for the interaction is local in the chi variable. And then finally, because this is a massless scalar field, we expect that this kinetic term here only depends on the difference squared, and that the potential is independent of chi. So of course, if this was a scalar field with some potential, then it could be a fair bit more complicated. But because it's a massless scalar field, the actual value of chi itself doesn't matter. All that matters is how it changes. So that's why we have this dependence here in quadratic term and no dependence in the potential term. So this is how we add a scalar field to the group field theory. And I think I'll stop here. I'll go over this quickly again on Thursday, but here at least you have an idea of how it's possible to include a scalar field. And of course, this is necessary if you want to do cosmology because you have to have some matter field there. Any questions?
Okay, yeah, so again, one more call for questions.
Mm-hmm.
Seems that there are no more questions, so then one more question. Which symmetries lead to the form of K and V?
Right. So the reason for that is if you look at, let's say, the action for a massless scalar field, it's really just the partial phi all squared. That's the action. And so what that means is that the action only knows about differences in chi. Right. So again, you have your massless scalar field chi. You have an action partial of chi all squared, and you can look at its equations of motion, and it only cares about the derivative of chi, only about how chi changes. So it doesn't matter if you start at chi is equal to 0 or chi is equal to 100. What matters is how much does it change by. So that's why we can't have the any term in the action that depends on chi alone. It can only depend on differences of chi. And it doesn't matter whether it increases or decreases, because again, it's in the action, you have the partial of chi all squared. So if chi increases or decreases, for the action, it's the same thing. So that's why there's a square here. The overall sign doesn't matter. And then the rest of the structure is determined by that. Because again, we're localizing chi in the Spinfield model on vertices. So that means that if you just look at the GFT potential, you're looking at all the terms that arrive at a vertex. So you'll have 5 of them. They all have to have the same chi when they meet there, because you've discretized the scalar field in such a way that it has a specific value at the vertex, the Spinfield vertex. And similarly, if you have an edge between 2 vertices, then you could have chi1 here and chi2 here, and then it can only depend on the difference between the values at the 2 vertices. So that's how we choose this value of k here.
Okay, thank you. There's another question. How to impose symmetries like homogeneity and isotropy for cosmology if we have abstract graphs not defined on a space-time manifold in GFT?
Right, exactly. And that's a very good question. And I'll be talking about that later. That's essentially why we're interested in condensate states. So a condensate state is one where all of the excitations are in the same state. So if you have a Bose-Einstein condensate, then all of your excitations, all of your, usually we think of particles, but here, of course, their quantum geometry are all in the same state. And so by having a state which is composed of all of these identical quantum geometry, then we can identify that with a spacetime which is homogeneous and isotropic. So that's why we choose to look at condensate states eventually. But you're right. I mean, in general, this is a difficult question of asking what GFT state corresponds to what large scale spacetime. So in general, we expect there to be some coarse graining, right? You have some microscopic description, which is possibly very, very complicated. And then you do some coarse graining, and then at larger scales, you see something that looks like a spacetime with the symmetries that you're interested in. In general, that's a hard problem.
Okay, thank you. So time is over and there are no more questions. So then let's thank you again for this nice lecture.
You're welcome.